Hi children. In this class, we are going to review chapter 4, somewhat lengthy chapter from the entire 11th and 12th standard topic, chemical bonding and molecular structure. Okay, a rapid revision on chemical bonding and molecular structure. Can we start? Ready? Yes. See, all of you know what is meant by a chemical bond. A chemical bond means a force of attraction that is holding different species in a given matter. That is called a chemical bond. Chemical bond basically we can categorize into two important segments. One is strong force of attraction. We may call it as primary forces. Primary forces. It is nothing but ionic bond, covalent bond, coordinate bond, even though it is an obsolete idea, coordinate bond, also called a dative bond, metallic bond. These are somewhat stronger in nature, permanent in nature. We may call it as a primary type of bonding. While there are weak forces of attraction, which may be called as secondary type of bonding. Secondary forces, which are basically weak forces of attraction. You know, weak van der Waals forces of attraction. Weak van der Waals forces of attraction. You might have heard about dispersion forces. The so-called London forces. Then dipole forces. Dipole attraction. Then induced dipole attraction. Right? And then special type of dipole attraction, hydrogen bonding, and then ion dipole attraction. These are some sort of secondary characteristic bonding, that is somewhat not permanent in nature, somewhat make and break type bond, right? So we have bonding may be categorized into two segments, primary bonding and secondary bonding. Primary bonding we are going to discuss in detail in the chapter ionic bond. Going to be discussed in detail, so-called electrovalent bond, electrostatic forces of attraction, coulombic forces, that is ionic bond, electrovalent bond, and a detailed talk on covalent bond, of course. And dative bond, we are not going to discuss in detail here. Of course, dative bond and its characters are coming in the complex chemistry. In the normal molecules, this we can consider as an obsolete idea, dative bond. And then metallic bonding, we are of course discussing in some other chapters, solid state chemistry and all, right? A detailed talk, comprehensive discussion on ionic bond and covalent bond. Of course, I'll tell you what is coordinate bond, metallic bond, etc. And secondary forces of attraction, only hydrogen bonding we are discussing in the chapter at the end portion of the chapter, while all others we are discussing in another chapter. Hope all of you know it is coming as a discussion in the chapter 5th chapter, states of matter, right? Which one? Van der Waals force of attraction, so-called dispersion forces, London forces, dipole attraction, dipole induced dipole attraction, ion dipole attraction, etc. Right? So, a detailed talk on one by one. First one, ionic bond. What is ionic bond? All of you know what ionic bond means. Ionic bond is formed by transfer of one of the electron from an atom to another atom. That is ionic bonding. It is formed by the transfer of one or more of an electron from one atom to another atom. Right? One or more electron transferred from one atom to another atom. An atom losing electron or giving electron will be converted to cation. An atom gaining electron will be converted to anion. Typical example known to all. If you take sodium, atomic number 11, it is 281. This is the inner configuration and this is the valence shell configuration containing one electron in the valence shell. And it loses that one electron. It loses that one electron and is converted to Na plus. And now it is having 10 electrons, 2-8 system. You know what is the importance of 2-8 system? That 2-8 configuration. One of the very important explanation forwarded by Hostel and Lewis, in which they said every atom tried to get, by undergoing a chemical bonding, every atom tried to get 8 electrons in their valence shell. And they were considering a system to be like a cube, where the corners of the cube with the 8 electron system giving some extra stability. That was the pictorial view they had, and is called the octet theory. All of you know octet theory. What is octet theory? A theory suggesting that atoms are combining, atoms are undergoing chemical combination, and thereby they are trying to get 8 electrons in the system. I'm sure all of you know there are so many molecules which are violating from octet system. We will discuss on the course of time. Here, sodium, by losing the valence electron, it is getting octet, and thereby it is converted to a cation. Meanwhile, if you take chlorine, atomic number 17, it is 287. It will accept one electron. This is losing one electron. This is accepting one electron and is converted to an anion. Thereby, this also get 288 system. Now, once again, you can see 287 turn 288. It is getting octet in the valence shell. Right? And thereby, there is a force of attraction holding Na plus cation and Cl minus anion, and we get an ionic solid, Na plus Cl minus, which is a ionic compound. This is a ionic compound. And ionic compound is formed by cation anion, by transfer of one or more electron from one atom to another. Here, in case of sodium and chlorine, sodium loses one electron and chlorine gains one electron. So, effectively, we can say one electron is transferred from sodium to chlorine. Not necessarily always one electron, it can be 2 electrons. For example, if you take calcium oxide, calcium is converted to Ca2 plus. Calcium atom is converted to Ca2 plus by losing 2 electrons. It is losing 2 electrons, and thereby it gets octet. While oxygen is converted to O2 minus. So here it loses 2 electron and get an octet system with the calcium 2 plus, and oxygen is gaining 2 electron and thereby it is converted to O2 minus anion, and thereby it is getting octet. I don't have to tell you, atomic number of oxygen 8, it is 26 turns to 8, gaining 2 electrons, octet is completed. So in this scenario, calcium loses 2 electron, oxygen gain 2 electron. So one or more electron is transferred from one atom to another, and thereby the atom losing electron converted to cation, atom gaining electron converted to anion, and thereby this cation anion makes a interaction between them, and that is electrostatic force of attraction, that is Coulombic force of attraction, that we call it as electrovalent bond, and that we call it as ionic bond. And this is electrovalency. This is the electrovalency. And this is what? Ionic bond. All of you know. Right? And then what is covalent bond? How a covalent bond is formed? A covalent bond is formed by A covalent bond is formed by mutual sharing of one or more pair of electrons, which we call it as bonded pair of electrons, bond pair electrons. It is formed by the mutual sharing of one or more one or more pair of electron between two atoms. For example, formation of H2 molecule. Hydrogen comes with one electron, another hydrogen comes with one electron, and there is a mutual sharing of electron, and we represent as HH. And this electron pair, we call it as bond pair electrons. Not necessarily one electron pair. If you take chlorine, again Cl2, it is like this. This is the Lewis electron dot structure of chlorine. 7 valence electrons of chlorine represented around the symbolic representation. And we have another chlorine atom with again 7 valence electrons. And these electron pair is shared mutually. We have once again a single covalent bond, because one pair of electron is involved in bonding. And we have 3 lone pair each with the chlorine. All of you know this is called the bond pair electrons, while this is called the lone pair electrons. Non-bonded pair of electron, that is called the lone pair of electrons. So whether hydrogen or chlorine, you can find one electron pair is bonded. What about if it is oxygen? What about if it is oxygen? You can see the scenario is slightly different. If you take O2 molecule, this is O2 molecule, 2 oxygen atom, which are binding like this. I'm sure you agree what I am drawing is called a Lewis electron dot structure. Lewis electron dot structure. You see what is happening here? The overlapping happens like this. A pair of electrons are involved in bonding. A pair of electrons are involved in bonding, and you can find there is OO double bond. OO double bond. There are 2 bond pairs, and the rest you can find the lone pairs. Why? Because here 2 pair of electrons are involved in bonding. Here also we can find they are trying to get octet. Not necessarily with hydrogen. Hydrogen cannot get octet. Simple atoms like hydrogen, lithium, etc. They may not, beryllium, boron, etc. They may not satisfy octet condition. All of you know, especially hydrogen never. Hydrogen can go only for duplet system. It can go with the helium system, duplex system. So this is a double bond. Here you can find there are 2 bond pairs, and 1, 2, 3, 4 lone pairs are present. Similarly, when you try N2 molecule, all of you know it is N triple bond with a lone pair each with each nitrogen atom, like this. So understanding to draw the Lewis electron dot structure, it is very, very important. How to draw the Lewis electron dot structure in covalently bonded molecules? That is very, very important, right? For example, if you take some heterogeneous system, say for example CO3 2-, you can see the valence electrons of carbon, 4 valence electrons. Oxygen, you know, there are 6 valence electrons into 3. There are 3 oxygen atoms, and this is of course in the valence area 2 electron. So 4 valence electrons from carbon, 6 valence electron each from oxygen into 3, and 2 electrons which are there as the outermost charge available. So it will be 4 plus 18 plus 2, you get 24 electrons, which you can distribute in such a way that you give carbon, oxygen, oxygen, oxygen. You can distribute across the atoms. You can distribute across the atom that the 24 electron distributed in such a way that you can see all are getting octet. The carbon and the surrounding oxygen atoms are getting octet. How it is possible? It is possible only in one possible distribution, which is somewhat like this. You see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 electrons so distributed, 12 electron pairs. That means 24 electrons. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 electron pairs are distributed in such a way that every atom gets octet. How they are getting octet? Please see that. Now this oxygen having octet 1, 2, 3, 4, 8 electron system. Carbon is getting 1, 2, 3, 4, 8 electron system. This oxygen getting 1, 2, 3, 4, 8 electron system. And this oxygen will also get a 1, 2, 3, 4, 8 electron system. And thereby we can represent carbon oxygen double bond, single bond with the minus and a single bond with the minus, as it carry a formal charge minus. This is the electronic distribution in carbonate molecule. And once again, not necessarily always the double bond is here. The double bond can be here also. And the O minus will come here. The double bond can be here and the O minus will be coming here. Modern reviews suggest that this is not the actual shape. The actual shape of the molecule is like this. This is the actual way the planar system of the molecule is represented according to the modern reviews what we learn in science. This is the planar system, the so-called carbonate. And not necessarily always the carbon oxygen bond is like this. It can be here, it can be here. And that means this electron structure may be represented with multiple forms. We are unable to represent with a single structure. And that phenomenon we call it as resonance. Resonance. What is resonance? Such a molecular species can give you resonance. Resonance is indicated with such an arrow. You see the resonating structure? I am representing this double bond over here. It can be like this, no problem at all. It can be like this. Two oxygen minus are coming here and the neutral oxygen is coming at this position. So this is called structure 1 and this is called structure 2. We call it as canonical structures, resonance structures. Where does this comes? When we are unable to represent a molecular species with a single Lewis electron dot structure, right? We can have one more structure. All of you know there is one more structure. How is that the third structure coming? Carbon oxygen bond is coming here and the remaining O minus will be represented here. This is O minus represented. The neutral oxygen comes at this position and that is the third resonating structure. We call them as resonance structures. We call them as canonical structures. Then which is the real structure? Is it 1? Is it 2? Is it 3? Science say that none of these are real structures. They are non-real structures. They are canonical structures. Then what is a real structure? Real structure lies somewhere in between the three and that is called a hybrid structure. The real structure lies somewhere in between the three represented like this and is called a hybrid structure. This is the hybrid structure. This is the resonance structure, resonance hybrid, which lies somewhere in between the three characters. All the three characters consolidated or merged together. That is hybrid. You know what the meaning of hybrid. So structure 1, non-real structure. Structure 2, non-real structure. Structure 3, non-real structure. And this is the hybrid structure. And the phenomenon, we call it as resonance. There are a lot of molecules which are able to perform like this. The very famous benzene molecule giving resonance non to all benzene molecule unable to be represented with a single structure. Is this structure or is this structure? Both are okay. Both are okay for benzene. These two are the canonical structures of benzene, while the actual structure, the hybrid structure, we represent like this. So where is the double bond? Is it here or here? Where is the double bond? Is it here or here? Is it here or here? The double bond is uniformly distributed across all the carbon-carbon 6 carbon atom. So that means, sir, is the bond identical in character? Exactly. The carbon-oxygen 3 bonds are identical. The carbon-oxygen 3 bonds are identical. The carbon-carbon 6 bonds are identical, equal in length, equal in character. That is resonance. Resonance averages the bond characters. Resonance averages the bond characters, and there are a lot of molecules which are able to perform resonance. Is it clear? So that is the way we draw the Lewis electron dot structure. At times we come across molecules like carbonate. We are unable to represent with a single structure. We will be going for multiple structures, and that phenomenon we call it as resonance. Hope it is clear. These are the topics which actually going through the initial portion of the chapter. These things we were talking all the way now. Drawing Lewis electron dot structure, you should practice. Covalent bond, the idea of covalent bond was postulated by Langmuir. And these are various Lewis electron dot structures which you can practice drawing. And this is carbon monoxide, nitrogen, nitrous oxide, etc. This is an important topic. Formal charge, an important topic, formal charge. Finding formal charge, that is a very, very important topic. How to find the formal charge of an atom in a Lewis structure. How to get the formal charge of an atom in a Lewis structure. The formula you can make use is total number of valence electrons of free atom minus total number of lone pair minus half into total number bond pair. Or you can make use, it is the difference between number of valence electrons of an atom in an isolated or free state and number of electrons assigned to that atom in the Lewis structure. Either you can apply this formula or you can think about this. The difference between valence electron of free atom and the number of electron assigned to that atom in the Lewis structure. Let us investigate how to find the formal charge, how to get the formal charge. For example, what is the formal charge of this carbon atom? What is the formal charge of this carbon atom? You can easily identify. Formal charge is equal to valence electrons of the atom, free atom. Valence electrons of carbon, all of you know, 4 minus lone pair electrons. Do we have any lone pair in carbon? Do we have any lone pair in carbon? No, it is 0 minus half the bond pair electrons. Half the bond pair electrons. How many bond pairs are there? 1, 2, 3, 4. There are 8 bond pair electrons. I repeat, 1, 2, 3, 4 pairs. 8 electrons are there. So it is half into 8. You are getting 4 minus 4. This will come out 4. You get 0. And the formal charge of carbon is 0. That way you can find out. Or you can think difference between valence electrons of the free atom and the number of electrons assigned in the structure. You see, valence electron of carbon 4. How many electrons assigned in the Lewis structure? 1, 2, 3, 4. 4 electrons are assigned for carbon. So it is 4 minus 4, 0. Now what about oxygen? What about oxygen? How to find the formal charge of oxygen? We know the formal charge is given here, minus 1. How to calculate? You see, formal charge of this oxygen, that is valence electron of oxygen in the free state, 6 minus number of lone pairs. There is 1, 2, 3 electron pairs, lone pairs, 3 into 2, 6 lone pairs minus half into bond pair. How many bond pairs? How many bond pairs? This is bond pair. This is bond pair. So it is 2. So how much you get? 6 minus 6, half into 2, you are getting minus 1, and that minus 1 is indicated here. Or you can think in another way. What is that? Valence, free number of valence electrons in the free atom. How many valence electrons in the free atom? 6. Minus number of electron assigned in the structure. How many electrons are assigned? 2, 4, 6, 7. 2, 4, 6, 7 electrons assigned in the structure. So it is 6 minus 7, you get minus 1. Is it clear? That's the way to find the formal charge. Right? So either you can apply this formula. What is the formula? Valence electron of free atom minus lone pair electrons minus half into bond pair electrons. That formula you can use, or you can simply think the difference between valence electrons and the electrons assigned in the structure. Is that okay? Right. For species like oxygen, nitrogen, finding formal charge is very simple. You know, oxygen is a divalent species. So neutral oxygen will be like this, and ionic oxygen will be 2 minus, O2 minus. If there is one bonding, it will be minus. If there are two bonding, it will be neutral. And the two bonding can be like this, it will be neutral. If there are three bonding, it will be plus. I repeat, neutral oxygen atom. And this is oxide ion. Imagine there is one bond, it will be O minus. Imagine there are two bond, neutral. Imagine there are two bond, neutral. Imagine there are three bond, it will be plus. Imagine the three bonds are like this, it will be plus. So any structure given to you, simply looking at the structure, you've been able to identify what is a formal charge. This is neutral atom, this is charge 2 minus, this is charge minus 1, this is neutral, neutral, this is formal charge plus, this is formal charge plus. What about nitrogen? What about nitrogen? Nitrogen, neutral atom. And you know nitride ion, it is N3 minus. What if there is one bonding? It will be 2 minus. What if it is two bonding? It will be minus. What if it is two bonding like this? Minus. What if it is three bonding? Neutral, because it is trivalent. What if it is three bonding like this? Neutral. What if it is three bonding like this? Neutral. What if it is four bonding? It will be plus 1. What if it is 4 bonding? It will be plus 1. Plus 1. Hope you understand. Plus 1. So nitrogen is trivalent. If there is one bonding comes, it will be 2 minus. Right? 2 bonding comes minus. 3 bonding, it will be 0. Like that, you can easily identify the characteristics of formal charge without calculation. Looking at the structural entity, you can assign the formal charge, which is very, very important. So what all things we have gone through so far? What is ionic bonding? What is covalent bonding? What is Lewis electron dot structure? What is octet theory? How to draw the Lewis electron dot structure? How to find the formal charge? What is resonance? And what is resonance structures, canonical structures? What is hybrid, resonance hybrid? These are topics we have gone through so far. Let me tell you a brief on what is meant by a dative bond, a coordinate bond. What is meant by a dative bond? Imagine you have an atom with a pair of electron and you have an atom with a B without any electron. Imagine they make a bonding, a mutual sharing of electron where the shared electrons are contributed by one atom. Then we draw like this. This is what called a coordinate bond. The donated electron pair belong to A, and that is mutually shared between A and B. That is called a dative bond or coordinate bond. A is called a donor atom, B is called the acceptor atom, and there is an arrow put from A to B, donor atom to acceptor atom. That is dative bond, that is called a coordinate bond. Coordinate bond in modern reviews can also be represented like this. Either you can represent like this or like this. That is the dative bond, that is a coordinate bond. Hope it is clear, right? So far, we were going through all the way this much. Already, we had a talk on all this area. This is what I was commenting earlier. Some limitation to octet rule. Limitation to octet rule. Always we can't expect in all molecules the atoms are getting octet. Look at the molecule. Look at the molecule LiCl, LiCl lithium chloride, beryllium hydride, boron trichloride. These are some molecules where they don't have octet. They don't have octet. In case of lithium chloride, you have only 2 electrons. Sorry. You have only 2 electrons here. While here you have across beryllium, you have 4 electrons. Across boron, you have 6 electrons. There is no octet. There is no 8 electron system. They are called incomplete octet. Incomplete octet. While certain molecules, there are odd electron system. Odd electron system. Look at nitric oxide, there is odd electron system. Look at nitrous oxide, there is odd electron system. These are few examples where there is no octet. Odd electron cannot be octet, no? There is no octet. So not necessarily in all molecules we suggest a concept of octet. There can be incomplete octet, there can be odd electron system, there can be expanded octet. There is a possibility of expanded octet. You see that? There is a possibility of expanded octet. This is expanded octet. Look at the around phosphorus. Around phosphorus in PF5. You can find bond pair 1, 2, 3, 4, 5. 5 pair means 10 electrons. Around sulfur, there are 6 pairs, 12 electrons. Around sulfur in sulfuric acid, there are 6 pairs, 2, 3, 5, 6. 12 electron system. So these are certain molecules where we'll go for expanded octet. So there is an incomplete octet, there is an odd electron system, there is an expanded octet, not necessarily always octet. Is it clear? Right. Now what the next topic? Ionic bond, this is already we have discussed. This is already we have discussed. An important topic, lattice enthalpy. What is meant by lattice enthalpy? That's a very important topic. Lattice enthalpy. What is lattice enthalpy? It is very important topic connecting to a ionic crystal basically. Ionic substances basically forming a crystal lattice. Lattice enthalpy means amount of energy required to break 1 mole of a crystal lattice to get individual isolated gaseous ions. That is lattice energy or lattice enthalpy. You can understand like this. NaCl in the solid state splitting to Na plus in the gaseous state, Cl minus in the gaseous state. The energy needed for this, that is called a lattice enthalpy. Amount of energy required to break 1 mole of crystal lattice to provide individual isolated gaseous ions. That is called a lattice enthalpy. For sodium chloride, the value is 788 kilojoule per mole. That is lattice enthalpy. Greater the lattice enthalpy influences greatly on solubility and various other properties. How does solubility affected by lattice enthalpy? Many of you may be aware of. Greater the lattice enthalpy, lower the solubility. The two important thermodynamic feature that explains the solubility of ionic solids, lattice enthalpy and hydration enthalpy. Greater the lattice enthalpy, lower the solubility. Lower the lattice enthalpy, higher the solubility. Similarly, hydration enthalpy. Hydration enthalpy means amount of energy released when 1 mole of ions hydrated, solvated. Greater the solvation enthalpy, greater the solubility. So what is the primary criterion to understand the solubility of ionic solids? The one with having low lattice enthalpy and high hydration enthalpy will be highly soluble. I repeat, the one with a low lattice enthalpy and a high hydration enthalpy will be highly soluble. Right? So that's an important point regarding ionic solids in particular. While next we have some bond parameters, bond length, the equilibrium distance between the nuclei of bonded atoms, that is called bond length. All of you know this is bond length. If you take chlorine molecule, this is chlorine molecule. This is chlorine molecule and this is one chlorine molecule. The distance between the two nuclei, the equilibrium distance between the two nuclei, that is called bond length. 198 picometer. That is bond length of chlorine molecule. And half of which already you may be learned about, half of which that is called a covalent radius. The distance between the two nucleus bonded is called a bond length and half of that distance is called a covalent radius for same type of atoms, covalent radius. Meanwhile, this distance from this nucleus to this nucleus, that distance and half of that is called van der Waals radius. You know this, covalent radius, van der Waals radius, always van der Waals radius will be pretty greater compared to covalent radius. Covalent radius comes in the range of 100 picometer. This is in the range of 180 picometer. Almost double it comes, right? Now we were talking about bond length. Bond length means the equilibrium distance between the nuclei of bonded atom is called bond length. Bond length influences bond strength. Greater the bond length, lower the bond strength. All of you know. So that is one important bond parameter to have a talk from the area. Then what? Bond angle. Bond angle. What is bond angle? The angle made by the atoms in a molecule is called bond angle. In water molecule, hydrogen atom, oxygen atom, hydrogen atom. The bond angle made by the hydrogen, oxygen, hydrogen, that is called bond angle. Bond angle explains various properties like dipole moment, polarity, etc. are explained by bond angle and its characters. Bond angle. Then it is bond enthalpy. What is bond enthalpy? Energy required to break one mole of a particular type of bond is called bond enthalpy, called bond dissociation enthalpy. Energy required to break one mole of a particular type of bond, that is called bond enthalpy. In some cases, it may also be referred as atomization enthalpy. Look at this example. HH, hydrogen H2 means HH. The energy required to break that bond, somewhat 435.8 kilojoule per mole energy is required to break one mole of HH bond. That is called bond dissociation enthalpy or bond enthalpy. In this scenario, it may also be called as atomization enthalpy as it is giving atoms, isolated atoms. This is bond enthalpy for oxygen. You can find it is pretty higher compared to this because it is a OO double bond. Meanwhile, NN triple bond, very much evident from the data, 946. So as the number of bond increases, bond enthalpy increases because the strength of the bond increases. So this is single bond, this is double bond, this is triple bond, NN triple bond, very tough to break. And it is the value required, value comes out to be 946. While in some cases, we go for average bond enthalpy in some cases. For example, if you take water molecule, there are two identical bonds. If you go for water molecule, there are two identical bonds. You see water molecule which is HOH. Breaking one bond, you get H and OH. And the value is 502, breaking one oxygen hydrogen bond. Now you have OH, from which H and O is liberated, you get a value 427. There are two bond dissociation enthalpies. As all of are aware, there are hydrogen oxygen bond, there are two bonds. The value for two bonds will not be same because they are breaking not simultaneously. One is broken and then the next is broken. When one is broken, the characteristic of the system changes. So naturally, the value will be different. So breaking first bond, breaking second bond, you get different value. Then how do you take the bond enthalpy? You go for average. That is called a mean bond enthalpy or average bond enthalpy. We take A plus B by 2. We take the average 502 plus 427 by 2. This is the average bond enthalpy of water molecules. What if you are taking methane? What if you are taking methane? Tell me, what will happen? Very simple. There will be 4 values. Here the bond is broken. Value A kilojoule per mole. Here it is B kilojoule per mole, C kilojoule per mole, D kilojoule per mole. And the value will be A plus B plus C plus D divided by 4. You go for average. Average bond enthalpy. So these are some important bond parameters. Not over. There is another one. Bond order. Bond order. Bond order. What is bond order? Bond order means number of bond between the atoms is called a bond order. Number of atoms between the bond is called a bond order. Number of bonds between the 2 atoms in a molecule is called a bond order. As we were viewing in the previous case, HH single, that is bond order equal to 1. OO double bond, bond order equal to 2. NN triple bond order is 3. All of you know, right? So, if you take H2, bond order is 1, O2, bond order is 2, N2, bond order is 3, CO, bond order is 3, like that. Very important point is that isoelectronic molecules have identical bond order. Isoelectronic species will have identical bond order. N2, CO, NO, they have isoelectronic character. Number of electrons remain the same. They will have same bond order. That's a very important question. A general correlation useful for understanding the stability of molecules is that with the increase in bond order, bond enthalpy increases and bond length decreases. With increase in bond order, strength of the bond increases, stability increases, bond enthalpy increases, bond length decreases. So bond order and bond length are inversely related. Okay, that's about the bond parameters. And about resonance, already we had a talk. About resonance. These are the resonating structure in ozone molecule. Resonating structure in ozone molecule. This is canonical structure number 1 and this is canonical structure number 2 and this is the hybrid structure. This is resonance hybrid structure. If you take OO single bond 148 picometer, OO double bond 121 picometer. But you see, in actual ozone molecule, every OO bond is identical and same. It is 128 as the bond parameters are made average. Resonance averages the bond parameters. Resonance averages the bond parameters. Right? So that is about resonance. That is about various bond parameters. This is carbonate molecule and this resonance already we have illustrated in the class. Now polarity of the bond. What is meant by polarity of the bond? See, the bond can be polar or non-polar and the molecule can be polar or non-polar. Very simple example, if you take HH, this is a non-polar molecule. This is a non-polar molecule as there is no charge separation, same atoms. What about Cl? If you take Cl, it is a non-polar molecule. There is no polarity, there is no charge separation. While if you take HCl molecule, there is polarity, there is charge separation. Hydrogen H plus and chlorine Cl minus. Because chlorine is more electronegative than hydrogen. This is what called polarity. Polarity means a charge separation. It is measured in mu. The property measured expressed in mu. This is magnetic moment, dipole moment. Mu equal to charge into distance. Either you can represent charge in coulombs. This is the partial charge in coulombs. And this is bond length in meters. So the unit will be coulomb meter. Or the charge can be electrostatic units or distance in centimeter CGS system. It is ESU centimeter. Or commonly you can use dBi units, known after Peter dBi. dBi units. E is the charge across the partial charge separation across the atom, and D is the bond length. D is the distance between the atoms. That gives you polarity in terms of dipole moment. Not necessarily always a molecule having polarity, having polar bond, having a dipole moment. Not like that. Many times it may get cancelled also. You can see if you take beryllium chloride. If you take the molecule beryllium chloride, this is beryllium chloride. There are two beryllium chlorine atoms. This is delta minus, this is delta plus. This is delta minus, again this is delta plus. There is a polarity indicated in this direction. And there is a polarity indicated in this direction. And the two vectors, the two forces are equal and opposite, will be mutually cancelled. And the net dipole moment found to be 0. And the molecule is non-polar. So the molecule contains polar bond, but the overall molecule is non-polar. If you take BCl3, the same scenario happens. The three dipole moments, the three polarity gets cancelled mutually across the 120-degree bond angle, and the molecule is non-polar. Dipole moment is 0 and it is non-polar. So the structural entity, the structural identity of a molecule and the polarity has got a great influence. If you take molecules, say for example, benzene with one chlorine here and one chlorine here, and benzene with one chlorine here and one chlorine here. This is having a net dipole moment, while this is having no net dipole moment. This is polar, while this is non-polar. How is that possible? How is that possible? It is because of the structural importance, structural way it is available. Here you have a polarity in this direction and polarity in this direction and a net polarity in this direction. While here you have a polarity in this direction and equal polarity in this direction will be mutually cancelled as it is coming 1,4 opposite position. Here it is 1,2 adjacent position. Hope you understand. So a molecule with the dipole moment, a molecule with the polar bond may not have net dipole moment. So here there is a polar bond, 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 but overall this is zero dipole moment. Sorry, this is zero dipole moment and this is a non-zero dipole moment. This is polar molecule, this is a non-polar molecule, like that. So care should be taken answering this kind of area and the concerned questions. That we can very well find over here. This is the dipole moment charge into distance of separation. It can be expressed in dBi units. It can be expressed in dBi units. 1 dBi is equal to 3.3 into 10 raised to minus 30 coulomb meter. 1 dBi is equal to 3.3 into 10 power minus 30 coulomb meter. Or in CGS system, 1 dBi is equal to 10 power minus 18 ESU centimeter. So CGS system unit also may be encountered in some problems. You be careful doing that. So you see the molecule BF3, the net dipole moment comes out to be 0. BEF2, net dipole moment comes out to be 0. While in water molecule, there is a net dipole moment, a reasonably good dipole moment, 1.85 dBi, because polarity in this direction and this direction, we have a net polarity in that direction, like that. Okay. There is an important comparison many times came for exam. There is an important comparison regarding the dipole moment of ammonia and NF3. This is ammonia molecule and this is NF3. We know fluorine. Fluorine highly electronegative. When highly electronegative fluorine comes, it is expected that dipole moment increases, but unfortunately, the scenario is opposite. In ammonia, the dipole moment is 4.9 into 10 power minus 30 coulometer, while in NF3 it is 0.8 into 10 power minus 30 coulometer. There is a difference. There is a difference that this is lower value. This is lower value than this because in ammonia, there is nitrogen, hydrogen, and the polarity is towards nitrogen. Polarity towards nitrogen, polarity towards nitrogen, and a lone pair is always away from central atom. So it is, you see, 3 dipole moment pointing upward. This is also upward, and there is a net dipole moment like this. So 3 moment upward, and lone pair is also upward. There is a net excellent dipole moment. What about in NF3? In NF3, it is from nitrogen to fluorine, nitrogen to fluorine, nitrogen to fluorine, while lone pair is away. So 1 is away, 1 is up, and 3 down. There is some sort of cancellation. Therefore, the net dipole moment will be a lower value. You see, 4.9 versus 0.8. 4.9 versus 0.8 means somewhat 5 times. Somewhat 5 times difference when you compare the dipole moment this versus this. That's a very important aspect. Okay. So far we were going through ionic bond, covalent bond, bond parameters, lattice enthalpy, bond length, bond enthalpy, bond order, resonance, drawing the electron door structure, formal charge, polarity. So many things. Now there is another very important point which is Fajans rule. Fajans rule. Covalent character and Fajans rule. The percentage covalent character and Fajans rule governed by a phenomenon polarization. Polarization. What is polarization? Imagine you have a cation and an anion. When they are far apart, they have an interaction, you know. Ionic bond, electrostatic force of attraction. Imagine the 2 species are coming close. When they come close, imagine this anion come close vicinity of cation. What will happen is the anion will go for a deformation like this. The anionic charge getting a deformation. So this symmetrical, the deformation of symmetrical electron density of anion when comes to the proximity of a cation is called polarization. The unsymmetric deformation, a deformation in the symmetric electron density. This electron density is symmetric. A deformation in the symmetric electron density of anion when it comes close to the proximity of a cation is called polarization. Polarization lead to covalent character. Greater the polarization, greater the covalent character. Polarization is caused by cation and caused on anion. Polarization is caused by cation and caused on anion. Greater the polarization, greater the covalent character. A small cation will have a high polarizing power. A small cation will have a high polarizing power. A large anion has got a high polarizability. So if you have a small cation and a large anion, polarization will be very high and covalent character will be very high. If you take group 1 alkali metal and group 17 halogen, lithium the smallest cation and iodine the largest anion, if you take Li, it is found to be most covalent. Small cation, largest anion. Smaller the cation, higher the polarizing power. Larger the anion, higher the polarizability. And greater the covalent character. Hope you get the point. Meanwhile, if you take cesium and fluorine, larger cesium and a smaller fluorine, the ionic character will be greater. Covalent character and ionic character are inversely related. So a small cation, larger anion, greater the polarization, greater the covalent character. Suppose you take same species. Suppose if you take FeCl2 and FeCl3, this will be more covalent than this because this is 2 plus, this is 3 plus. A 3 plus cation will be smaller in size and greater the covalent, greater the polarization. A small cation can cause greater polarization, greater covalent character. Medium can influence a covalent character. If you take AlCl3, in CS2 it will be covalent, in water it will be ionic. This is a polar medium in which this will be more ionic. This is a non-polar medium, this will be covalent. Medium can influence nature. Aluminum chloride in CS2 remain covalent. Aluminum chloride in polar water medium, it is ionic. So size of cation, size of anion, charge of cation, medium. And imagine you have compound MClX and NClX. Just imagine. Where M is a S block metal and N is a D block metal. Just imagine. You have two chlorides. One is S block chloride, one is D block chloride. And the metals are almost identical characters. Then the one with the D block character will be more polarizing than S block, and that is found to be more covalent. These references are concluded as Fajans rule. Fajans rule explaining percentage ionic and covalent character. I think it is pretty clear. Okay, right. Now, there is some important theories coming in the chapter. Mainly 3 theories we are governing and explaining in the chapter. One is called VSEPR theory. One is called VB theory, valence bond theory. And the final one is molecular orbital theory. Okay, 3 important theories. Let's have a look at one by one. First one, VSEPR theory. Valence shell electron pair repulsion theory. Proposed by Sidgwick and Powell, and later on further modified by Nylom and Gillespie. These are the postulates of VSEPR theory. Very important. Important postulates of VSEPR theory. Number 1, you can see the shape of the molecule depends upon number of valence shell electron pairs around the central atom. The shape of a molecule is decided by the number of electron pair, whether lone pair or bond pair, around the central atom. Point number 1. Point number 2. Pair of electrons in valence shell repel one another since the electron clouds are negatively charged. Each electron pair repel each other. Point number 2. Point number 3. They tend to occupy maximum space away from each other surrounding the central atom because they repel each other. Since they are repelling each other, they will try to, suppose there are 2 lone pair, they will try to occupy away, as far away as possible. Next one. The valence shell taken as a sphere with electron pair localizing on a spherical surface at a maximum distance. Same point. Next one. That's an important point. A multiple bond treated as if it is a single electron pair. A multiple bond treated as if it is a single electron pair, and we call them as a super pair. For example, if we are talking about a molecule, say POCl3, it's basically having, the modern review says, this is the molecule POCl3. How many electron pair around the central phosphorus? You see, 1, 2, 3, 4, 5. No, it is only 4. This is taken as this is a multiple bond, taken as a single electron pair. And we call it as super pair. So it is 1, 2, 3, 4. 4 electron pair surrounding the phosphorus decides the shape of the molecule. That is the very popular one, tetrahedral. So the shape of the molecule is decided by the number of electron pair across the phosphorus atom. Hope you get the picture, right? Now, where two or more resonance structures are represented, the model is applicable to any structure. That we know. In resonant characters, the multiple, we are unable to represent with one structure. It can be applied on another structure. That is called canonical structures, resonance structures, right? A very, very important conclusion is also made from the theory. That is also very important point. You see, all of you know this. The kind of repulsion. Are the electron pairs maintaining same kind of repulsion? No. Lone pair repulsion is maximum. Then lone pair, bond pair repulsion. Then bond pair repulsion, which is minimum. Based on this context, we can have molecular shapes explained by VSEPR theory. Let's have a look at one by one. Here BeCl2, we have two electron pairs. This is beryllium. This is two chlorine atom maintaining linear shape 180 degree. This is Bf3, three electron pairs, boron central and 3 fluorine makes a 120 degree planar system. This is methane, central carbon with 4 hydrogen atom maintaining 109.5 degree tetrahedral system. While this is PCl5, phosphorus and the surrounding atom makes a trigonal bipyramidal geometry. Let's have a look at one by one. Through the tabulated array, we have concern to the VSEPR theory, the important table of information. This is the important tabulated array. Let's go through one by one. Number of electron pairs, 2. And the arrangement will be like this. A, the central atom, one pair to left, one pair to right, linear system, 180 degree. Example, BeCl2, HgCl2. Next, 3 electron pair, trigonal planar. Across the central atom, it comes like this, trigonal planar by bond angle 120 degree. Example, Bf3. Very simple to understand. Now it is 4 electron system, that is making a tetrahedral arrangement. All of you know what is meant by tetrahedral arrangement. It comes like this. This is tetrahedral arrangement. All bonds are identical, making a bond angle 109.5 degree. Example, very popular, methane. Then 5 electron pair, trigonal bipyramidal, PCl5, trigonal bipyramidal. You can see across the central atom, 3 bonds are in a plane, B. They are in the equatorial plane, while one B up, one B down, that is axial bonds. All of you know axial bonds are more elongated than equatorial bonds. As equatorial bonds, they are far away making 120 degree angle. But the other one, the bond angle is only 90 degree. When the bond angle decreases, very important point. When the bond angle decreases, that will affect the bond length. Bond length will increase. And that's why axial bonds are getting elongated compared to planar bonds in PCl5. So they have unequal bond length. Okay. Next is 6 electron pair, that is octahedral system. The central atom we have in a plane and 4 surrounding atoms in the same plane, and one above the plane, one below the plane. We call it as octahedral geometry. The very famous example, SF6. All bonds are identical. Right? Sulfur at the center, fluorine 1, 2, 3, 4, 5, 6. That is octahedral geometry. So linear 180 degree, trigonal planar 120 degree, tetrahedral 109.5 degree, trigonal bipyramidal 3 120 degree and 2 90 degrees, and octahedral all 90 degrees. Respectively with electron pairs 2, 3, 4 up to 6. Right? This is without any lone pair. There is no lone pair available. This is without any lone pair. No lone pair electrons. Now we are going to review with the lone pairs how it comes. That is in the next table. With the lone pairs, how it is going to be. molecule type, number of bond pair, number of lone pair, electron arrangement, shape and examples. So the molecule type AB2E type, 2 bond pair and 1 lone pair. A means central atom, B means surrounding atom, E means lone pair electrons. A for central atom, B for bond pair, E for lone pair. 2 bond pair, 1 lone pair will be like this, 2 bond pair, 1 lone pair, and the molecular shape is bend shape. Bend shape. So, it's not like that, it is SO2, SO2 or O3. That's a printing error. It is SO2 and O3. They make a bend shape. They make a bend shape. Next one. Next one, AB3E type. A 3 bond pair and 1 lone pair. 3 bond pair and 1 lone pair. It will be tetrahedral arrangement. 1, 2, 3, 4. But the shape is trigonal pyramidal. Look at this. This is trigonal pyramidal. It's coming like this. Ammonia. Trigonal pyramidal. Example, ammonia. Now the next is A. It is not AB3E2 type. It is AB2E2 type. 2 bond pair and 2 lone pairs. 2 bond pair and 2 lone pairs. Again, it will be a tetrahedral system, but the molecule is bend in shape. Look at that. This is bend in shape. Bend shape. For example, water molecule. 2 bond pairs and 2 lone pairs. So, as the number of lone pairs are getting introduced, it go from regular geometry to non-regular geometry. Okay. So, you need to review all these examples and the type of molecule in the table. Next, it is AB4E type. AB4E type. 4 bond pair and 1 lone pair. 4 bond pair and 1 lone pair. It is available like this 1, 2, 3, 4, 5, and the shape is seesaw shape. Hope you understand. This is called a seesaw shape. This is seesaw shape. Example SF4. AB4E type. AB4E type. Next one AB3E2 type. 3 bond pair and 2 lone pair. Total 5. 1, 2, 3, 4, 5. Again the same system, but the shape is T shape. This is T shape. Bend T shape. Example ClF3. Remember, bend T shape. Sir, why bend T shape? Bend T shape because there is lone pair. Lone pair will always create a disturbance in the regular geometry. Okay, that's it. Next it is AB5E type. AB5E type. 5 bond pair and 1 lone pair. 5 bond pair and 1 lone pair. Total 6 electron pair making octahedral arrangement. But the shape of the molecule is square pyramid. You see square pyramid. This is square pyramid. Square pyramid. 1 lone pair. Example BRF5. Again, not a regular square pyramid. Not a regular square pyramid as there is a lone pair is present. Why I am insisting on that? Because there was question previously asked, how many 90-degree bond angles in this molecule? If you try to answer 90-degree, 4 in the plane and 4 above the plane, it's wrong. 4 plus 4, 8. It's wrong. Answer is 0. There is no 90-degree bond angle because it is not a regular geometry. The presence of lone pair makes it irregular. Okay. And the last one, AB4E2 type. 4 bond pair and 2 lone pair will be octahedral like this, and it is square planar. This is a regular geometry as the 2 lone pair effect is getting cancelled mutually. That is a square planar geometry. So these tabulated informations with examples and kind of molecules make a thorough analysis regarding the understanding of VSEPR theory of the shape of the, regarding the explanation regarding the shape of the molecules, VSEPR theory and the subsequent explanations. Okay. And there are more illustration of examples which you can go through. Next is VB theory, valence bond theory. VB theory, valence bond theory, introduced by Hitler and London, further developed by Linus Pauling, VB theory. According to VB theory, when two atoms are coming close, the valence shell electrons of atoms getting paired up and they are getting bonded up to give a stable molecular system. For example, if you take up H plus H giving H2, this is one hydrogen atom, this is one hydrogen atom with one electron present, and this is another hydrogen atom with another electron present. When they are far apart, there is no force of attraction between the atoms when they are far apart. And the forces operating now is this nucleus. This is nucleus A and this is electron A. There is an attractive force. This is nucleus B and this is electron B. There is a force of attraction. So the attractive force is always existing. NA attracted by EA, NB attracted by EB. Our point is, imagine these two atoms are coming close. When they come close, what will happen? When they come close, new forces start operating. What are the new forces? This nucleus start attacking this electron. And this nucleus start attacking this electron. Right? A new forces of attraction starts operating. There is NA-EA attraction always. There is always NA-EA attraction. There is always NB-EB attraction. Now, the two new attractive forces are NA starts attracting EB and NB starts attracting EA. And that attractive forces increases and at an optimum distance, they start binding each other. They are getting bonded each other at an optimum distance. And the two electrons comes in the common region, pairing up, and thereby we get HH, that is H2 molecule, where the potential energy, the energy drops to a minimum and they get stabilizes at an optimum distance. And that optimum distance is called bond length. This is bond length, 74 picometer. That is bond length, very important. They can't come more close than that. They can't come more close than that. That's an optimum minimum distance. If they try to more come close, there will be more repulsive forces, because apart from the attractive forces, there are repulsive forces. What are the repulsive forces? NA repels with the NB, EA repels with the EB. There are important repulsive forces also operating. So the attractive force dominate at an optimum distance when they bond up. This is what the kind of explanation given by VB theory, with the energy reference also that is available from this diagram. You can very well see the diagram arranged. You see that the molecules, when they are far apart and as they come close, what happens to the energy? You can easily understand. You see the earlier explanation and this energy level diagram. Compare the earlier explanation and this energy level diagram. The two atoms far apart, as they comes close, this is intermolecular distance, internuclear distance. The two hydrogen atom coming close, you can see the energy drops. They come close, energy drops. At an optimum distance, bond length 74 picometer, where the energy drops to a minimum, you can find they are binding to each other. This is the bonded situation and this is the bond length. If the bond length decreases further, the energy shoot up. Why the energy shoot up? Because of the repulsive forces. This is what VB theory suggestion. This is what the VB theory suggestion is. Valence bond theory suggestion is. At an optimum distance, the system gets stabilized by bonding them each other with the pairing of valence electrons. That is valence bond theory. Valence bond theory. Right? And this dropped energy, that is nothing but bond energy. This is the bond energy of hydrogen. This is the bond energy of hydrogen. If you give this much of energy, you can break that bond. If you give this much of energy, you can break that bond, because forming that bond, that much of energy dropped. Energy dropped means energy released. If you supply that much of equivalent energy, you can break HH bond. That is called the bond energy, which we have seen already. And the kind of orbital overlap that are possible is also explained in the same area. This is the kind of overlap, very important. This is the kind of overlap. It's better I take a picture and we'll review from there. These are the kind of orbital overlap which are possible. You see the kind of overlap? There is positive overlap. There is positive overlap. There is negative overlap. This is positive overlap. This is negative overlap. And there is zero overlap, out of phase overlap. What is meant by positive overlap? Very simple. Symmetric overlap is called a positive overlap. Symmetric overlap. Plus lobe overlap with the plus lobe. Two orbitals overlap in such a way that symmetric lobes are overlapping. Plus with the plus. Plus with the plus. Plus with the plus. Plus with the plus. That is called a positive overlap. Constructive overlap. I'm sure all of you know a bond, atomic orbital bonding like this, axial overlapping called a sigma bond. This is a sigma bond. Axial overlapping of orbitals. This is axial overlapping called a sigma bond. This is axial overlapping sigma bond. This is a lateral overlapping pi bond. The lateral sideways overlapping is called a pi bond. This is called a pi bond. This is a sigma bond. This is also pi bond. Now, whether sigma or pi, same orbitals overlap. I mean, same lobes overlap, not same orbitals. Same orbital, same lobes are overlapping. Symmetric lobes are overlapping. Plus lobe with plus lobe. Plus plus, plus plus or minus minus. Plus plus with the minus minus. That is called a positive overlap. That is called a symmetric overlap. Suppose the overlap is plus and minus. That is called a negative overlap or out of phase overlap, unsymmetric overlap, unstabilized overlap. This is a stabilized overlap. This is a destabilized overlap. You see, plus and minus overlap, negative overlap. Plus and minus overlap, negative overlap. Plus and minus overlap, negative overlap. While there is a zero overlap, the one which is not possible. How can this overlap is possible? How come the nodal point of p orbital interact with s orbital? It is not possible. So p orbital like this and s is trying to bind over the nuclear region. No, that's a zero overlap. How come px overlap with the py? This is px and this is py. How come they overlap? You see, pz makes a sigma bond. px pi bond. px pi bond. pz makes a sigma bond. px makes a pi bond. py makes a pi bond. How come px and py interact? They cannot. Px and py cannot interact. That's a zero overlap. So these are the molecular overlapping, right? So positive overlap, negative overlap, zero overlap. Okay. And this is sigma bonding, SS overlapping, sigma bonding, SP overlapping, sigma bonding, PP overlapping, sigma bonding. All these you can find it is through the axis. It is through the axis. This is through the axis, sigma bond. This is through the axis, sigma bond, axial overlapping. This is through the axis, sigma bond, axial overlapping. While pi bond means sidewise overlapping is called a pi bond. Sidewise overlapping is called a pi bond. And this is a pi bond, right? Now, the most important topic from the chapter, hybridization. That is the next important topic, hybridization. See, hybridization introduced by, explained by Linus Pauling. According to Linus Pauling, what is hybridization? Commented. The phenomenon defined as the process of intermixing of atomic orbitals of slightly different in energies so as to redistribute their energies, resulting in the formation of new set of orbitals of equivalent energy and shape. It's a theoretical idea introduced by Linus Pauling. According to him, what is hybridization? It is the intermixing of atomic orbitals having slightly difference in their energy and shape, which is happening on the central atom of a covalent molecule, and thereby we are getting a redistribution of orbitals giving equivalent number of new orbitals having identical shape and energy, and they are distributed across the central atom, around the central atom, giving definite geometry to the molecule. So basically hybridization happens on the central atom on a covalent molecule. It is happening by the intermixing of atomic orbitals having difference in their energy and shape, so that you are getting new orbitals equivalent in number, and they are distributed around the central atom, giving a definite geometry to the molecule. And the new hybrid orbitals are of same energy, same shape. For example, suppose we are talking about one of the mostly encountered hybridization, say in methane molecule. In methane molecule, where the central atom is carbon surrounded by 4 hydrogen atoms. You know carbon atomic number 6, 1s2, 2s2, 2p2, and this is the valence orbitals 2s2 and 2p2. This is the electronic configuration of carbon. We know carbon is tetravalent. How carbon is tetravalent? Very simple. Just upon excitation, one of the electron may be shifted to this orbital and you get one electron here, and p orbital contain one each electron. Now you have 4 orbitals ready to make a bond. Now what are the 4 orbitals? This is s orbital, spherically symmetrical. This is px orbital like this, and the other one is py orbital like this, and the third one is pz orbital. This is s orbital, 2s orbital. This is 2px orbital, 2py orbital, 2pz orbital. Imagine the 4 hydrogen atom comes and make a bond. So hydrogen atom number 1, that is 1s orbital. All of you know hydrogen having 1s electron. Imagine one hydrogen comes and binding here. Now the next hydrogen, 4 hydrogen atom. Next hydrogen comes and bind here. Next hydrogen comes and bind here. Next hydrogen comes and bind here. 4 hydrogen atom comes and bind across around the carbon central atom with 4 different orbitals. S orbital, 1 hydrogen, that is SS linkage. Then p orbital through the x-axis, px orbital and s orbital. Then py, pz. We can see that the 4 bonds will not be equivalent in nature. Primarily speaking, the one is SS orbital, SS linkage. This is s orbital linkage. The other 3 are s orbital, p orbital linkage. They are going to be different. Never we can accept SS linkage and SP linkage are same. But we know, experimentally we know, evidence we have, methane having tetrahedral geometry, the first tetrahedral geometry of methane established by Van Hoff. This is the tetrahedral geometry of methane. All 4 bonds are identical and equivalent. All the 4 bonds, carbon hydrogen bonds, are identical and equivalent with a bond angle 109.5 degree. How that can be established? It is explained by the concept of hybridization introduced by Linus Pauling. what he says is, it is not the pure orbitals interacting with the hydrogen atom. Before interaction, they undergo an intermixing, and that intermixing lead to four new orbitals which are having identical shape and equivalent energy, and we call them as sp3 hybrid orbitals. How that name came? sp3, one s orbital and 3 p orbital, sp3 hybridization. And now we have four new hybrid orbitals. The shape can be represented like this, and they are surrounding the central carbon atom, giving a definite geometry to the molecule. How is that? The central carbon atom with one hybrid orbital, another hybrid orbital, another one, and the fourth one. All four orbitals are identical and equivalent. And now the hydrogen atom comes and make a bonding. And now we can understand, see, hydrogen atom, four hydrogen atom. One hydrogen atom makes a bonding here, another hydrogen atom makes a bonding here, another hydrogen atom makes a bonding here, last one makes a bonding here. Now we can understand all the four bonds are equivalent and identical. They are directed in space such a way that their repulsion is minimum and the distance is maximum. That lead to a definite geometry, giving a shape to the molecule, tetrahedral geometry. And this phenomenon, we call it as hybridization. Hybridization is intermixing of atomic orbitals in a central atom of a covalent molecule, having slightly difference in energy and shape, to give new equivalent number of orbitals, which are identical shape and energy and directed around the central atom, giving a definite geometry to the molecule. This is hybridization. All of you learned. And now, what are the different kind of hybridization we come across, right? What are the different type of hybridization? This is sp3 hybridization. What are the other type of hybridizations? So, sp3 means one s orbital and 3 p orbital, giving sp3 hybridization. The shape of the molecule is tetrahedral in shape. It is tetrahedral in shape, and the bond angle is 109.5 degree. That is the bond angle. sp3 hybridization. How came sp3? One s orbital and 3 p orbital. Right? What are the other cases? You see the next one, there is sp2 hybridization. What is sp2 hybridization? One s orbital and 2 p orbital. It is formed by one s orbital and 2 p orbital. That will be sp2 hybridization. You will be getting 3 new hybrid orbitals. All hybrid orbital we can represent like this. 3 new. Why 3 here? S orbital and 2 p orbital. sp2 hybridization. How is going to be the geometry? For example, BF3 sp2 hybridization. Boron central atom, one orbital like this, one orbital like this, one orbital like this. This is sp2 hybridization, making a bond angle 120 degree. It makes 120 degree bond angle. It is trigonal planar in nature, or triangular planar, making a bond angle 120 degree. So sp3 tetrahedral 109.5 degree. sp2 there are 3 orbitals, 3 bonding around the central atom. It is triangular planar. Okay. What about sp hybridization? Third one. sp hybridization. It is by one s orbital and 1 p orbital. You are having 2 new hybrid orbitals. Example, BeCl2. One beryllium, the central atom, and one orbital to left, one orbital to right. You have chlorine and chlorine, making a bond angle 180 180 degree and the molecule is linear. So sp hybridization, linear molecule 180 degree. sp2 hybridization, triangular planar 120 degree. sp3 hybridization, tetrahedral 109.5 degree. sp means one s orbital, one p orbital. sp2 means one s orbital, two p orbital. sp3 means one s orbital and three p orbital. Like that. Is that over? No, there are many cases. There are many cases. The most prominent cases that we discuss in the chapter is sp linear 180, sp2 planar 120, sp3 tetrahedral 109.5 degree. Next is sp3d. sp3d, that is the next one. sp3d hybridization. sp3d hybridization, one s orbital and 3 p orbital and 1 d orbital, preferably d z square orbital, which lies in the internuclear axis. Right? That makes sp3d hybridization. That means you have 5 new hybrid orbitals. Example, PCl5. Phosphorus, the central atom. 1, 2, 3, 4, 5. Already it is learned. Trigonal bipyramidal geometry with the 3 bonds in the plane and the 2 axial bonds. Trigonal bipyramidal geometry which maintain 120 degree across the planar system and 90 degree across the axial system. There are 2 90 degree angles, two 90 degree axial bond, right? And 3 120 degree bonds in the plane. Right? So how many 90 degree per molecule? How many 90 degree per molecule? It is 390 degree on top. Each planar bond will make a 90 degree. 390 degree on top and 390 degree at the bottom. 3 plus 3, 6. So 6 90 degree angle, 3 120 degree angle, and axial bond will make a 180 degree one angle. 180 degree one angle. Example, PCl5. Trigonal bipyramidal geometry. Trigonal bipyramidal geometry. Another very prominent one is sp3d2 hybridization. sp3d2 hybridization. Next one. sp3d2 hybridization. What is meant by sp3d2? 1 s orbital, 3 p orbital, and 2 d orbital. What are the 2 d orbitals? Preferably dz square 1 orbital and dx square minus y square 1 orbital. So axial orbitals are more involved in hybridization primarily. Right? So it is 1 s orbital, 3 p orbital and 2 d orbital. A total of how many? A total of 6 hybrid orbitals. How are they allocated? Example, sulfur hexafluoride. How are they allocated? 1, 2, 3, 4, 5, 6. The 6 orbitals are allocated in such a way that it makes a octahedral geometry. All 90 degree bond angle. All bonds are equivalent, identical 90 degree. Unlike this case, axial bonds are more elongated than planar bonds. Here, all the bonds are equivalent and makes a 90 degree. How many 90 degree per molecular system? See, it will make a 90 degree on top with the axial bond. It will be making 4 90 degree with the axial bonds. Planar bonds. So how many? 4 90 degree from the top. Within the plane, there is 4 90 degree. And below the plane, there is 4 90 degree. So it is 4 plus 4 plus 4. 12 90 degree bond it will make. And how many 180 it will make? You find out. Okay. So these are the most important hybridization that we discuss in the chapter. SP, SP2, SP3, SP3D, SP3D2. We can have one more. SP3D3 hybridization. SP3D3 hybridization. 1 s orbital and 3 p orbital and 3 d orbital. Example, IF7. sp3d3 hybridization. So how is going to be making? You can see, you can have a regular pentagon in a plane. You can have a regular pentagon in a plane and the iodine in that plane, and 5 bonds in the plane, and 1 bond above the top of the plane and 1 bond below the plane. So it will be IF7 coming like this. IF7 coming like this. We call it as pentagonal bipyramidal. Pentagonal bipyramidal. sp3d3 hybridization. sp3d3 hybridization. 7 bond will be coming, and the 7 bond, 5 will be in the plane, 1 to top of the plane, 1 to bottom of the plane. What will be the bond angle? Of course, the axial bond will make 90 degree. What going to be in the planar system? You find out. So these are the prominent cases of hybridization. A very important topic from the chapter. In the previous topic, we were going through various atomic BB theory, various orbital overlapping related topic, and hybridization also related to the same topic. And probably winding up in the chapter, the last topic coming is molecular orbital theory, MO theory, very important and modern theory, MO theory. So these are the area from the chapter you can find the hybridization being dealt, various talk on hybridization. And the last topic is MO theory explained by Hunt and Mulliken. MO theory 1932. Explained by Hunt and Mulliken. MO theory, molecular orbital theory, point number 1. Electrons in an atom is present in atomic orbitals. Electrons in a molecule are present in molecular orbitals. Point number 1. Point 2. Atomic orbitals of comparable energy and proper symmetry combine to form molecular orbitals. Molecular orbitals are obtained by the combination of atomic orbitals. So in an atom, electrons are present in atomic orbitals. In a molecule, electrons are present in molecular orbitals. Point number 1. Molecular orbitals are formed by the combination of atomic orbitals. Point number 2. Point number 3. What is the third point? In an electron in an atomic orbital influenced by one nucleus, while electron in a molecular orbital influenced by more than one nuclei. In atomic orbital, electrons are monocentered. In a molecular orbitals, electrons are polycentered. What is the meaning of that? What is the meaning of that point? You see, hydrogen atom. This is hydrogen atom, and this electron is governed by one nucleus. What about hydrogen molecule? H2. H2, all of you know it is HH. It is like this. This is HH. You can very well understand the electronic system is governed by two nucleus. You see, this is the electronic system I am drawing. The symmetric electronic system is governed by two nuclei. This is monocentric and this is polycentric. Here electrons are monocentric. Here electrons are dicentric, polycentric. So in an atom, electrons are monocentric. In a molecule, electrons are polycentric. In an atom, electrons are present in atomic orbital. In a molecule, electrons are present in molecular orbital. Molecular orbitals are obtained by combination of atomic orbital with the proper energy and symmetry. Atomic orbitals are monocentric, molecular orbitals are polycentric. What is the next point of postulates concerned to the theory? Let's have a look at it. Very, very important one, next one. The number of molecular orbital formed is equal to number of combining atomic orbitals. As many atomic orbitals combine, as many molecular orbitals are formed. If two atomic orbitals are combining, you get two new molecular orbitals. And the one is called a bonding molecular orbital and the other is called a anti-bonding molecular orbital. Bonding molecular orbital is stabilizing in nature. Anti-bonding molecular orbital is destabilizing in nature. I will explain in detail how is that to be understood. If we take the case of hydrogen atom and hydrogen molecule, Suppose we are taking hydrogen atom 1 and hydrogen atom 2 forming hydrogen molecule. Two hydrogen atom forming hydrogen molecule. How we can understand the molecular orbitals? All of you know hydrogen having 1s1 system. This is 1s1 system for hydrogen atom 1. And the other hydrogen atom, there is 1s1 electronic system. So this is one hydrogen atom and this is another hydrogen atom. This is atomic orbital of one hydrogen atom. This is atomic orbital of next hydrogen atom. They are going to combine. When they combine, you get two new molecular orbital. One is with the lower energy and one is with the higher energy. One with the lower energy called a bonding molecular orbital, sigma 1s. Bonding molecular orbital. One with the higher energy called anti-bonding molecular orbital, sigma star 1s, ABMO. BMO means bonding molecular orbital, stabilizing orbital, lower energy orbital obtained by the constructive interference of atomic orbitals. All of you know atomic orbital is to be considered as a wave function. This is atomic orbital psi A for the first hydrogen atom. This is atomic orbital psi B for the second hydrogen atom. They can interfere in two ways. Psi A plus psi B. That is called the psi molecular orbital, bonding molecular orbital. And psi A minus psi B, that is giving psi MO. That is anti-bonding molecular orbital we represent with a star. So interference of atomic orbitals, interference of atomic orbital wave functions can take place in two ways. One is addition interference, one is constructive interference, one is destructive interference called subtractive interference. So this is constructive interference, addition interference. This is destructive interference, subtractive interference. Constructive interference lead to the formation of stabilizing orbital called a bonding molecular orbital. The other one makes a destabilizing orbital called anti-bonding molecular orbital. So this is bonding molecular orbital with a lower energy compared to the combining atomic orbital. With a lower energy compared to the combining atomic orbital, and this is destabilizing orbital with a higher energy compared to the combining atomic orbitals. When electron coming to this, the molecule is stabilized. When electron going to this, the molecule is destabilized. Electron entering here will increase the stability of the molecule. Electron entering here will decrease the stability of the molecule. This is obtained by addition interference. This is obtained by subtractive interference. So MO theory is in coordination with the quantum mechanical aspect of atomic structure, molecular structure, electronic structures. Okay. So what happens in a hydrogen molecule? In a hydrogen molecule, these two atomic orbital combine, we get two new molecular orbital, sigma 1s, sigma star 1s. So how is the configuration? H2, you know, there is two electron, and the two electron, this and this, will be utilized here. The filling of molecular orbital happens in the same way as we do in atoms. In atoms, electronic configuration, we have learned, or every one of us know, of Bohr principle, Pauli's exclusion principle, Hund's rule of maximum multiplicity. The same things we can apply over the electronic configuration of molecules also. For example, hydrogen. Hydrogen with the two electrons will enter into lower energy orbital, sigma 1s. So the configuration will be sigma 1s to sigma star 1s0, which will help you to understand this is a diatomic species. This is a two electron system, paired electron system, and it is diamagnetic in nature. I was about to comment that. Diamagnetic in nature. It is a diamagnetic species, no unpaired electrons present. Moreover, you can find the bond order. How to find the bond order? Bond order is equal to NB minus Na by 2. I am reminding you how to find the bond order. Number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital divided by 2. That means number of electrons in bonding molecular orbital 2 minus number of electrons in anti-bonding molecular orbital 0 divided by 2. You are getting 1 as the bond order, and it is HH single bond. HH single bond. MO theory help us to identify, to find out the bond order, stability of the molecule. Then paramagnetic or diamagnetic, all things we are able to understand. Okay. What if it is H2 plus? What if it is H2 plus? Suppose we are dealing with H2 plus. How many electrons in H2 plus? H2 plus. H2 contain 2 electron. H2 plus contain 1 electron. The configuration will be sigma 1s1, sigma star 1s0. Now it is paramagnetic in nature. H2 plus is paramagnetic in nature. H2 is diamagnetic in nature. What is the bond order? Bond order is equal to NB minus Na by 2. So it is 1 minus 0 by 2. You are getting fractional bond order. Earlier bond order is 1. Now the bond order is half. Right? What if it is H2 minus? What if it is H2 minus, which contain 3 electrons? How is the configuration? Sigma 1s2, sigma star 1s2. Sorry, sigma star 1s1. Sigma star 1s1. How is the configuration? This is the configuration. Sigma 1s2, sigma star 1s1. What is the bond order? Once again, it is paramagnetic in nature. What is the bond order? It is NB minus Na by 2. 2 minus 1 by 2. You are getting same bond order. So these two are almost same stability. Rather, this will be pretty more stable than this, because here one electron is there in anti-bonding orbital. Anti-bonding is slightly more destabilizing than the bonding do stabilize. I'll repeat. Anti-bonding orbitals are slightly bit more destabilizing than the stabilization caused by bonding molecular orbital. Here there is an extra electron coming in the anti-bonding molecular orbital, which causes more destabilizing than the electron caused by the bonding electrons. So both are almost equally stable, but this is slightly lesser stable compared to this. So MO theory help us to understand the molecular electronic configuration. MO theory help us to understand the bond order. MO theory help us to understand the magnetic properties, etc. Various advanced level informations are explained by molecular orbital theory. It helps us to understand why He2 does not exist. Why He2 does not exist? Helium 2 ion, we know, does not exist. We know helium is monoatomic. Why? Helium contain 2 electron, helium 2 contain 4 electron. It will be sigma 1s2, sigma star 1s2. And you have bond order equal to NB minus Na by 2. 2 minus 2 by 2, you are getting 0. Bond order 0. Means such a system does not exist. Bond order means number of bond between the atoms. Bond order 0. Such a species cannot exist. MO theory clearly comments a molecule can stable, a molecule can exist if and only if NB is greater than Na. This is the condition for stability. NB greater than Na. If it is NB equal to Na or NB less than Na, such a system cannot exist. This system cannot exist. NB less than or equal to Na. Such a system cannot exist. NB means number of electrons in bonding molecular orbital. Na is number of electrons in anti-bonding molecular orbital. Such a system cannot exist. These things are explained by MO theory. And winding up with MO theory and the topic almost, we need to understand the the molecular configuration for oxygen and nitrogen in particular. Very, very important. Oxygen and nitrogen in particular. What is the MO configuration for oxygen? What is the MO configuration for oxygen? O2 molecule. Let us try to understand. Oxygen. See, this is oxygen atom 1 and this is oxygen atom 2. All of us know oxygen atomic number 8 having 1s2, 2s2, 2p4. There is 1s orbital, 2s orbital, 2p orbital. So this is 1s orbital for the 2 oxygen atom. This is 2s orbital for the 2 oxygen atom. And this is 2p orbital for the 2 oxygen atom. So this is oxygen atom 1, 1s, 2s, 2p. This is oxygen atom 2, 1s, 2s, 2p. They are going to combine. How they are going to combine? As many atomic orbital combine, you get as many new molecular orbital. So S combine, you get sigma 1s, sigma star 1s. Okay. Now 2s combine, you get sigma 2s and sigma star 2s. So this is quite natural, quite same the way we were going through earlier. What about 2p? How is then going to combine? You know 2p is going to be like this, px, py, pz. So pz will make a sigma bond, px, py will make a pi bond. Pz will make a sigma bond, px, py will make a pi bond. Okay. So out of 2p, we have px, py, pz. Z will make a sigma bond. This is sigma 2pz. While x and y will make a pi bond. And this is pi 2px, pi 2py. And they will have same energy. They will have same energy. They are degenerate orbitals. Now the counterpart. It will be pi star 2px and pi star 2py. And the last one, sigma star 2pz. This is the configuration for O2 system. This is the configuration for O2 system. How is the configuration? Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, pi 2px, pi 2py, pi star 2px, pi star 2py, sigma star 2pz. How do you write the configuration? O2 containing 16 electrons. O2 containing 16 electrons. How do you write the configuration? Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px equal to pi 2py. Next, pi star 2px equal to pi star 2py and sigma star 2pz. How do you do the configuration? Yeah, it is 16 electron. 2, 2, 2, 2, 2 like this. You see, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2. Now 2, 4, 6, 8, 10, 12. We have left with how many electrons? Did I miss any orbital? Yes, I missed one orbital over here. Here we missed one orbital. Hope you understand. In between here, there is one orbital missing, isn't it? It is sigma 2pz. Sigma 2pz. It has to be like this, right? Sigma 1s, sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, then pi 2px, pi 2py, 16 electron, 2, 4, 6, 8, 10, 12, 14, 15, 16. The last two electron will be unpaired electron system. The last two electron will be unpaired electron system and distributed in pi star orbitals equally. Hund's rule of maximum multiplicity. If same energy orbitals are coming, the electron has to be distributed equally. Hund's rule of maximum multiplicity. Isn't it? Right. So this is the electronic configuration of O2 and clearly explained O2 is paramagnetic. O2 is paramagnetic with the two unpaired electrons. What is the bond order? How to get the bond order? Bond order is equal to, once again, Nb minus Na by 2. Nb minus Na by 2. What is the number of bonding electrons? 2, 4, 6, 8, 10. So it will be 10 minus 6 by 2. You are getting 2. O double bond. O double bond. Bond order equal to 2. Right? So this configuration for O2, very, very important. Not only for O2, you need to expertise doing what is O2, what is O2 plus, what is O2 minus, what is O2 2 plus, what is O2 2 minus. All this you need to work out using this configuration. Simultaneously, the configuration for N2 you need to by heart. What is the configuration for N2? One small change. N2 configuration, there will be a change over this region. So what is the configuration for N2? O2 N2 is most important two systems we need to consider. It will be sigma 1s2, sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, and now pi 2px, pi 2py, sigma 2pz, pi star 2px, pi star 2py, and sigma star 2pz. Only one change. Here it is sigma 2pz, pi 2px, pi 2py. Here it is pi 2px, pi 2py, then sigma 2pz. That's the one change. Maybe due to very small size in nitrogen, this change in energy is happening. And such flexibility is possible in MO theory, and that is helpful explaining the properties of various molecular systems, especially magnetic behavior, paramagnetic behavior explained on this ground. Let's see the configuration of N2. How comes the configuration of N2? There is 14 electron system, right? 14 electron system. So it will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2, sigma 2pz2. Isn't it correct? 2, 4, 6, 8, 10, 12, 14. And that clearly tells us N2 is diamagnetic. What is the bond order? Nb minus Na by 2. What is Nb? 2, 4, 6, 8, 10. So it is 10 minus 4 by 2. You are getting 3. And it is N triple bond. N triple bond. Bond order is equal to 3. Bond order you can even calculate in a very simple way. You see, these two will get cancelled. This is complementary system, will cancel. This is complementary system, will cancel. And you can take the remaining 2 plus 2, 4 plus 2, 6. 6 minus 0 by 2. 6 minus 0 by 2, you will get 3. That is also possible. Complementary electronic systems, you can cancel. That way also you can find out. Right? And here also, you may try to work out, you must try to work out what are the configurations for N2 already we did. N2 plus, N2 2 plus, N2 minus, N2 2 minus. All systems nitrogen and below, you will follow this configuration. All systems oxygen and above, you will follow this configuration. So the two configurations you need to memorize. Of course, there are some other cases. If you go to carbon monoxide and related cationic species, there is a slightly different configuration. MO theory is giving variety of differences in their explanation. But most important from the NCERT aspect, we need to go through is nitrogen and a lower species, oxygen and a bigger species, two important configurations. The other configurations, as and when it comes for the competitive purpose, we are going to discuss in detail in our classes. Okay, remaining all this you need to try. All oxygen species, all nitrogen species you need to try. At the same time, you can try working out what is B2 species coming, what is C2, etc. This kind of practicing, exercising to be done from MO theory, which is very important. You can easily keep it in mind. If an electron is added to bonding molecular orbital, the bond order will increase, stability will increase. If an electron is added to anti-bonding molecular orbital, bond order will decrease, stability will decrease. That's a very important point you can understand. You can keep it in mind. Suppose an electron, one electron added to bonding molecular orbital, bond order increases by 0.5. One electron added to anti-bonding molecular orbital, bond order decreases by 0.5. Similarly, one electron removed from bonding molecular orbital, bond order decreases by 0.5. One electron removed from anti-bonding molecular orbital, bond order increases by 0.5. Without working out the bond order, you can confirm what change in bond order is going to happen. Figure out whether the electron is added or removed. If it is added to bonding molecular orbital, bond order will increase. If it is added to anti-bonding molecular orbital, bond order will decrease. If the electron is removed from bonding molecular orbital, bond order will decrease. If the electron is removed from anti-bonding molecular orbital, bond order will increase. That also you can keep it in mind. A very, very important area from the chapter. And finally, a small topic on hydrogen bonding. What is meant by hydrogen bonding? It's a special type of dipole-dipole attraction wherein molecules like H2O, molecules like HF, molecules like ammonia, you encounter hydrogen bonding. The most electronegative fluorine with the hydrogen, the second most electronegative oxygen with the hydrogen, the third most electronegative nitrogen with the hydrogen, you get hydrogen bonding. It is nothing but hydrogen of one molecule which is bonded to highly electronegative oxygen is binding to the next electronegative atom in the molecule. So this hydrogen interacting with the more electronegative oxygen with the next molecule. This is hydrogen bonding. Similarly here, you see HF. The hydrogen bonded to one molecule with more electronegative fluorine is making an intermolecular interaction with the more electronegative fluorine of the next molecule. So hydrogen bound to fluorine, oxygen, nitrogen will interact with a similar hydrogen in the next molecule. That is called hydrogen bonding and is called intermolecular hydrogen bonding, one of the strong variety of dipole-dipole attraction. Is that okay? There can be intramolecular hydrogen bonding also. If you take molecule like nitrophenol, orthonitrophenol, this is orthonitrophenol, you can have intramolecular hydrogen bonding. You see that within a molecule there can be hydrogen bonding. Within a molecule, there can be hydrogen bonding. The hydrogen connected over here makes a hydrogen bonding with the neighboring OH group. Hydrogen makes a hydrogen bonding with the neighboring NO2 oxygen. So what is hydrogen bonding? A special type of dipole-dipole attraction. Who is involved here? Hydrogen. How it is involved? A hydrogen binded to very electronegative fluorine, oxygen, nitrogen is trying to interact with the next molecule electronegative part, giving a relatively stronger force of attraction, which is very, very important in many molecules, including proteins, biomolecules, etc. Finding a vital application, particularly in biomolecules, hydrogen bonding plays a vital application. Hydrogen bonding, there are two types: intermolecular hydrogen bonding between the molecules, intramolecular hydrogen bonding within the molecule. This is intramolecular. This is intermolecular hydrogen bonding. The most prominent examples are water molecule, HF, ammonia. Okay, so what are the main topics we have gone through from the chapter? We started from the various types of bonding: ionic bond, covalent bond, coordinate bond, Lewis electron down structure, drawing the electron down structure, formal charge, polarity, dipole moment, resonance. Very important word, resonance. Then polarization, covalent character, Fajans rule. Then the important theories: VSEPR theory, lot many molecular systems, VB theory, various types of orbital overlapping, hybridization, sp, sp2, sp3, sp3d, sp3d2, sp3d3, etc. Various other varieties we are going to discuss in the complex chemistry also. And finally, MO theory, molecular orbital theory, bonding molecular orbital, anti-bonding molecular orbital, expertising on various exercise doing on nitrogen, oxygen and other systems. And finally, about hydrogen bonding. These are the important area from the chapter. Okay, bye, see you.